Welcome to the deep dive. There's this question, it's everywhere right now, isn't it? On every news feed, in every boardroom chat, maybe even over dinner.
Yeah, definitely.
Are we like right on the edge of artificial general intelligence? And, what does AGI even really mean when you dig into it?
It's a huge question and often misunderstood.
So today, we're doing just that. We're embarking on a crucial deep dive into the absolute cutting edge of AI, specifically navigating this whole pursuit of AGI. We're going to sift through the insights, the really profound ideas from a leading voice here, François Chollet. You probably know him, brilliant mind behind the CARES framework.
It's a key figure,
Absolutely. To really unravel why the approaches from, say, the last 10 years, even with all their amazing successes, they didn't quite get us to that general intelligence.
Right.
And then what new breakthroughs are fundamentally changing the game now and what genuine machine intelligence might actually look like.
What's really fascinating here, and what we'll be digging into, is this pivotal shift, a real change in the AI paradigm.
A shift away from just bigger is better.
Exactly. We're moving beyond that somewhat simplistic idea that just making models bigger, feeding them more data, will somehow magically unlock true intelligence. It's just not panning out that way.
Okay.
Instead, the focus now is swinging towards a far more nuanced understanding of what intelligence itself actually is.
So our mission for this deep dive
Is to distill the core concepts, the things that authentically define AGI, and to really illuminate the paths researchers are taking now, the new direction.
focusing on things like new benchmarks, new theories.
Precisely. Groundbreaking new benchmarks and these theoretical frameworks that are seriously challenging our previous assumptions. It's a whole new landscape, really.
And why should this matter specifically to you listening? Because, this isn't just about understanding the latest tech headlines, right?
Yeah.
Knowing which company has the biggest model this week.
No, it goes much deeper.
It really cuts to the core of what it means to be intelligent, to solve problems, to learn, fundamentally, to think.
Yeah.
So whether you're maybe a seasoned tech enthusiast or a business leader trying to figure out what's next, or honestly, just someone curious about where humanity is heading.
Yeah, it impacts everyone eventually.
The insights we're about to unpack, they should give you a much clearer, more grounded picture of where AI is truly headed, what this AGI pursuit genuinely represents.
And it might even change how you think about your own problem solving, actually.
Interesting. Okay, so to really get where we're going, we first need to look back, right? Take an honest look at the journey so far.
Definitely need that context.
And the story of modern AI, especially this whole deep learning revolution, it's been profoundly shaped by one almost unbelievable fact.
Which is?
The relentlessly falling cost of compute. This isn't just a small trend we're talking about. It's monumental, exponential.
It's staggering when you look at the graph.
Picture this. Since way back in 1940, the cost of processing power has consistently plummeted by 2 orders of magnitude. That's a factor of 100 every single decade.
Every decade. For over 80 years.
And crucially, there's just no sign that this extraordinary rate is slowing down. So this incredible, almost dizzying growth in accessible compute power, combined with this parallel explosion of available digital data, that became the rocket fuel, the unignorable rocket fuel that just ignited the deep learning boom all through the 2010s.
That's a really powerful way to put it. And the impact of that combination, cheap compute, tons of data.
Yeah.
It was, frankly, transformative.
Right. Suddenly things that seemed impossible.
Exactly. Suddenly, deep learning models, leveraging these readily available GPUs and these massive data sets, they started making truly astonishing rapid progress on problems that had seemed completely intractable for decades.
Like what specifically?
Well, we saw breakthrough after breakthrough, particularly in fields like computer vision models, recognizing objects, faces, with almost scary accuracy. And natural language processing, too. Machines starting to understand, even generate, human language in ways that got more and more sophisticated.
Yeah, the progress there felt really fast.
And a pivotal moment within that whole era was the emergence of self-supervised text modeling. That was a game changer.
How so?
Because it let models learn from these vast amounts of unlabeled text. They essentially taught themselves by predicting missing words or sentences. No human labels needed, mostly.
Okay. Learning from the raw data itself.
Precisely. And that breakthrough led directly, almost inevitably, to the dominance of scaling up large language model training,
Right.
LLMs.
Right.
The entire research field, almost like in unison, just pivoted its focus towards that approach.
Yeah.
Bigger models, more text data.
And this scaling up strategy, this just relentless pursuit of bigger models, more data, it seemed like it was crushing everything, right? Every benchmark in its path.
It really did. And what was truly remarkable, maybe a bit insidious looking back, was how predictable the improvements seemed.
Predictable.
Yeah. Researchers would scale up their model size, feed it more and more training data, and almost like clockwork, bang, consistently better results on the established benchmarks.
And often using the same basic tech.
Often, yes. Even using the exact same underlying architecture, the same training processes. These were the now famous scaling laws. They seem to promise a clear path forward.
And that predictability, it must have created a really strong belief system in the field.
Oh, absolutely. The predictability of these scaling laws fostered a very powerful belief, almost an unshakable dogma within the AI community.
Like, just keep scaling.
Exactly. Just 2 or 3 years ago, the prevailing wisdom, the unquestioned assumption was basically more scale is all you need. Full stop.
Wow.
The idea was if we just keep making models bigger, training them on more data, we'd eventually solve everything. AGI would just emerge spontaneously.
So the field was obsessed with this idea.
Pretty much singularly obsessed with the notion that general intelligence would just kind of pop out by cramming more and more data into bigger and bigger models.
Yeah.
That was the absolute standard view, the consensus.
But now,
Looking at it today, with even just a little more time and experience, almost no one in the core research community believes that anymore. The dogma has crumbled fast.
And here's where it gets really interesting, right? Because there was this fundamental, deep problem with that scaling dogma all along.
There was a big one.
A deep, pervasive confusion between skill and intelligence. We were basically, and you could argue many still are, mixing up two fundamentally different things.
Okay, spell those out.
On one hand, you have memorized skills, things that are static, task-specific, essentially just pre-computed answers or routines.
Like knowing multiplication tables.
Exactly. And on the other hand, you have fluid general intelligence, which is that profound, dynamic ability to understand something you've literally never seen before, to make sense of it, adapt to it on the fly.
The difference between knowing the answer and knowing how to figure out the answer.
Precisely. Knowing how to figure out the answer to any new question, that's the key difference.
And to really pinpoint this critical difference, François Chollet, way back in 2019, this was well before LLMs really took off, before the scaling craze hit its peak.
Yeah.
He released a benchmark specifically designed to expose this gap. It's called the Abstraction and Reasoning Corpus.
ARC.
Or ARC1 as we call it now.
Okay, ARC1. Designed to test fluid intelligence, not skill.
Meticulously crafted for exactly that purpose.
Yeah.
And the results, even looking back now, they remain stark, incredibly telling.
So think about the sheer scale up since 2019, from those early models to something like, I don't know, GPT 4.5 or whatever the latest big one is.
It's immense.
We're talking, what, roughly a 50,000-fold scale up?
Yeah.
In compute data parameters. It's just astronomical.
It really is hard to wrap your head around that number, 50,000x.
Yeah.
And despite that astronomical scale up, despite these models basically inhaling the entire internet during training,
Their performance on ARC1
went from 0% accuracy back in 2019 to only about 10% by late 2023. Just 10%.
Wow. And humans. How do humans do on ARC1?
Oh, that's the kicker. Any human, even a 4-year-old child who gets the basic concepts, they'd score well above 95% on ARC1. Easily.
So it wasn't about regurgitating facts?
Not at all. That's the key. It wasn't about spitting back memorized information it saw during training. It was purely about his capacity to make sense of new, unseen problems. On the fly.
Problems outside its training data.
Exactly. Problems requiring genuine adaptive intelligence, not just bigger memory banks or faster lookup. And that 10% score, when humans are near perfect, that was a massive, big red flashing light.
Signaling that something fundamental was missing.
Screaming it, really, that the whole scaling approach on its own was missing something absolutely fundamental about intelligence.
So what does this all mean for the path to AGI? It really sounds like we needed completely new ideas, like truly novel concepts, beyond just scaling up pre-training and doing that static inference thing. That old path, the one that seemed so successful, it wasn't actually leading to general fluid intelligence.
No, it was leading us to bigger, faster calculators, maybe, more sophisticated parrots, not truly understanding minds.
Okay.
And that's precisely what started to happen.
Yeah.
In a really pivotal moment, one that I think few outside the core research community fully grasped at the time. Everything changed.
When was this?
Last year, 2024. the AI research community began to pivot dramatically to a new and fundamentally different paradigm.
Which is?
Test time adaptation, or TTA. This represents a really profound shift in how models are designed to operate, moving beyond just being static.
Okay, explain TTA simply for us. What does it actually mean for a model to adapt at test time? What's happening?
It means creating models that can literally change their own internal state, their own understanding, their capabilities, right when they're faced with something new, at the moment of inference.
So not just looking up an answer.
No. Think of it less like a static encyclopedia query and more like a dynamic learner, something that can adjust its very understanding as it goes. It's not just recalling preloaded knowledge from its training data. It's about the ability for the model to learn, to adjust, to adapt in real time to the specific novel data or problem it's seeing right now.
Like a human learning a new rule mid-conversation.
That's a great analogy.
Yeah.
Learning a new rule or concept and immediately applying it to the next sentence. That's the kind of dynamic capability we're talking about for machines. It implies a much deeper, more active form of understanding.
And the impact. What was the immediate tangible impact of this pivot towards TTA on that stubborn ARC benchmark?
Suddenly, almost instantly, significant progress started to be seen on ARC. This wasn't just like incremental gains. It was a qualitative leap, a breakthrough that really shocked the community.
Really? An example?
Yeah, a prime example was December 2024. OpenAI previewed their O3 model, and they had a version specifically fine-tuned on ARC itself. And for the first time ever, it demonstrated human-level performance on ARC1.
Human level on ARC1.
Wow. It wasn't just a blip. It was a pivotal, undeniable moment. It basically validated the whole TTA approach.
Yeah.
It showed that with the right paradigm, even tasks that seemed completely impossible just a year before were suddenly within reach.
So fast forward to today, here in 2025, it really feels like the landscape has just completely shifted, in the blink of an eye almost.
It really has.
We've gone from this era of brute force scaling to something fundamentally more adaptive.
Absolutely. Today, we have definitively moved on from pre-training scaling being the only path to intelligence. We are now fully, unequivocally, in the era of test-time adaptation.
This ability to modify itself dynamically.
Yes. Based on the specific new data it sees during inference, that is paramount now. It's seen as a core requirement to demonstrate genuine, fluid intelligence.
So it's not just a new feature, it's a whole new philosophy.
Exactly. A new philosophy of how AI systems should be built if we want them to truly learn and adapt beyond their initial training phase.
And what kinds of techniques fall under this TTA umbrella? What are researchers actually doing to make this happen?
Well, TTA covers a whole range of pretty sophisticated techniques, all aimed at this dynamic self-modification.
Such as?
Things like test time training itself, where a model effectively keeps learning, updating its internal parameters, even subtly on the fly, based on the specific input it's getting right now.
Yeah.
Then there's program synthesis, which is incredibly powerful. Here, the model isn't just tweaking numbers. It's actually generating new executable code or internal algorithms designed specifically to solve the problem at hand.
Like the AI becomes its own programmer for the task.
Pretty much. And finally, there's train-of-thought synthesis, which is a bit more abstract, but just as vital. Here, the model essentially tries to reprogram its own internal logic, its reasoning process, for the task. It's literally thinking through steps and adapting its internal approach. And get this, every single AI approach that performs meaningfully well on ARC today, every cutting-edge system, is using one, or usually a combination, of these test-time adaptation techniques.
So this is more than just a technical tweak then. It's a fundamental shift, something you really need to understand if you want to make sense of where AI is going.
Absolutely fundamental.
It means the path to AGI isn't just about building bigger models anymore. It's about building smarter, more adaptive, and ultimately more dynamic ones.
That's the new frontier.
But this leads us to an even deeper question, doesn't it? Almost philosophical. Before we can even seriously talk about building AGI, we have to grapple with the word itself. We have to ask, what is intelligence? What do we even mean when we say we're trying to build AGI if we don't define the target clearly?
We can't hope to hit it yet. This question, it has a long, often contentious history in AI and cognitive science.
Right.
And over the decades, two main, often conflicting lines of thought have kind of emerged to define intelligence and, by extension, the goals of AI research.
Okay, what are they?
On one side, you have what's often called the Minsky-style view, after Marvin Minsky, one of the AI pioneers.
Right.
This perspective largely says AI is about making machines capable of doing tasks that humans normally do.
The do what humans do view.
Pretty much. And this aligns very closely with the current mainstream corporate view, actually, which often defines AGI as a model that could do, say, 80% of economically valuable tasks currently done by humans.
So a very pragmatic, output-focused definition.
Very pragmatic. If an AI can basically do your job, or most jobs, then boom, it's AGI. That's kind of the gist in that view.
Okay. And the other view?
Then there's a contrasting perspective, often called the Maddie view, which François Chollet aligns with much more strongly.
And what does that say?
This view argues that the true essence of AI isn't just performing known tasks better or faster. It's about getting machines to handle problems they have not been specifically prepared for.
Dealing with novelty.
Dealing with something genuinely new, something outside their training, blazing fresh trails where no path exists yet. So Chollet sees intelligence not as like a collection of static skills you possess, but as a dynamic process.
Skill is the output, not the intelligence itself.
Exactly. Skill, in this framing, is just the output of that underlying intelligent process. So displaying skill, even at tons of tasks, doesn't by itself show true fluid intelligence. It shows proficiency, maybe, but not necessarily ingenuity or adaptability.
That distinction feels absolutely crucial, and it's something we probably gloss over all the time when we talk about AI.
Right.
It's like the difference between, I don't know, having a perfect roadmap versus owning the company that can build new roads anymore.
That's a fantastic analogy, really clarifying. Let's run with it.
All right.
A perfectly designed, extensive road network lets you travel super efficiently from point A to point B. For a specific predefined set of A's and B's, right, it's static. You follow the map.
That's skill, the output.
That's skill, the output of some past intelligent process. But a road building company, that company has the intelligence to connect new A's and B's on the fly, as needs evolve, as new towns pop up, if the terrain changes, if there's a new opportunity somewhere previously unreachable.
It can invent the past.
It invents the path. It doesn't just traverse an existing one. That's intelligence. So when we attribute intelligence to just a crystallized behavior like following the map or a static skill program, we're making a fundamental category error.
Confusing the process with the product.
Exactly. Confusing the engine of creation with its finished output. Don't confuse the road with the dynamic, adaptive process that created the road and, crucially, can build a new one whenever needed.
That makes so much sense. It really reframes the whole discussion. So if we try to formalize this a bit more, how does Chollet actually define intelligence from this process perspective?
He sees intelligence not just as a quality, but as something quantifiable, a conversion ratio.
A ratio between what?
Specifically, he defines it as the ratio between the information you have available. That's your entire past experience, all the data you've seen, any developer-imparted priors or built-in knowledge the system has.
Okay, all your inputs.
Right. Between that input information and your operational area over the vast space of potential future situations you might encounter.
Operational area.
Meaning, how broadly can you apply your knowledge? And crucially, these future situations will feature high novelty, significant uncertainty, things you haven't seen before.
So intelligence is how efficiently you handle the unknown future based on the known past.
Exactly. In simpler terms, intelligence is the efficiency with which you take your past information, your accumulated knowledge, and you operationalize it. You make it work to effectively deal with an unpredictable, novel future. It's an efficiency ratio. How much useful capability can you squeeze out of your experience to solve entirely new problems?
And this formal definition, it immediately highlights why using those traditional, almost always exam-like benchmarks for AI models might be a really misleading idea if AGI is the goal.
Profoundly misleading.
Yes, they just don't measure that kind of intelligence.
Precisely. Human exams were never designed to measure intelligence in this fluid, adaptive sense Chollet talks about.
Yeah.
They were designed, quite reasonably, to measure task-specific skill and accumulated knowledge.
Based on assumptions for humans.
Right, based on assumptions sensible for humans, but that just don't apply to machines in the same way. Like, most exams assume you haven't memorized every single question and answer beforehand.
Right, you're supposed to figure it out.
Yeah, you're deriving solutions on the spot. That assumption just breaks for machines. If an AI passes an exam just by memorizing the whole internet and then regurgitating the right info,
It's showing memory, not intelligence.
it's demonstrating scale and prodigious memory, absolutely, but not fluid intelligence.
Yeah.
It's performing a skill it has, effectively pre-computed, not reasoning through something genuinely novel.
Okay. So if we want to truly define and measure intelligence in a way that actually points us towards AGI, what are the absolute key concepts we have to keep in mind, beyond just benchmark scores?
There are three critical concepts, I think, that act as our guideposts here.
Okay, first.
First, there's that fundamental distinction we already touched on. Static skills versus fluid intelligence. Think of it as a spectrum.
Right.
On one end, you've got systems just accessing a huge library of pre-programmed solutions for known problems. Static.
Uh-huh.
On the other end, you have systems truly able to synthesize brand new programs or approaches on the fly for a problem they have never ever seen before. We need to measure where a system sits on that spectrum.
And it's not just on or off, right? There's a range.
Exactly. It's a continuum.
Right.
The second concept is what Chollet calls operational area.
We mentioned that briefly.
Right. For any skill a system has, there's a huge difference between being skilled only in situations very close to what it saw in training, that's narrow generalization,
Okay.
versus being skilled across a really broad scope of novel situations, that's broad generalization.
Like the driving example. Learning in one city versus driving anywhere.
Exactly like the driving example. If you learn to drive, you're able to handle any city, ideally, not just the specific streets you trained on. That adaptability shows a broad operational area.
And that's also a spectrum, from super specialized to broadly applicable.
Yes, absolutely. And lastly, maybe most critically, you have to look at information efficiency.
Efficiency. How much data or compute it needed.
Precisely. For a given skill or problem-solving ability, how much information, how much raw data, how much practice, how much compute did you need to acquire that skill or solve that problem?
Higher efficiency means higher intelligence.
Bingo. Higher information efficiency equals higher intelligence. If a system needs, hundreds of thousands of hours of training data and millions of dollars of compute to get a simple skill, a human picks up in minutes.
It's not very intelligent, even if it gets the skill eventually.
Exactly. It's demonstrating very low intelligence by this measure. If you need to check every single possible chess move to find the best one, you're using brute force, not intelligence. It's about the fundamental efficiency of acquiring and deploying skills, data efficiency, and compute efficiency. That efficiency is the real signal of underlying intelligence.
Wait, this raises a really important question then. Why do these precise definitions matter so much? I mean, it feels academic, maybe.
But it's not just academic, it's deeply practical.
How so?
Because as engineers, as researchers, as anyone trying to build something transformative, we can only truly build what we can effectively measure.
Right. If your measure is wrong.
If our measure of intelligence is fundamentally flawed, or measuring the wrong thing, then our progress will inevitably be misdirected. We'll optimize for the wrong target.
Okay.
The way we define and measure intelligence isn't just a technicality. It reflects our deepest understanding of cognition. It scopes out the questions we ask, and crucially, it predetermines the kinds of answers we'll get.
It's the feedback signal driving everything.
Exactly. It drives all our efforts, research, development towards our stated goals. And there's this phenomenon you see constantly in engineering, which Chollet calls the shortcut rule.
The shortcut rule. That sounds potentially bad.
It often is.
Yeah.
It's the inherent tendency that when you focus intensely, maybe almost singularly, on hitting one specific metric, one measure of success,
Yeah.
you might brilliantly succeed at hitting that measure, but you often do it at the expense of everything else not perfectly captured by that measure. You hit the immediate target, but you kind of miss the deeper point.
Sacrificing the forest for the trees, maybe?
Sort of like that, yeah. And we've seen this pattern play out repeatedly in AI history, often with unintended, sometimes ironic, consequences.
Give us some examples. Where has this shortcut rule tripped up AI?
Okay, think back to the famous Netflix prize competition. Remember that?
Vaguely, yeah. Better movie recommendations.
Right. The goal was purely
Yeah.
build the most accurate movie recommendation system based on a specific metric. The winning system was incredibly accurate, truly impressive by that metric.
Yeah.
But it was so incredibly complex, so computationally intensive, that it was totally impractical for Netflix to actually use in production. It never got deployed.
So they hit the target metric, but missed the real goal of a usable system.
Exactly. Hit the target, miss the point. Or think about AI in chess. Back in the 70s, 80s, the community really pushed for chess AI because they genuinely thought it would teach us fundamental truths about human intelligence, problem solving.
Right. That was the original motivation.
Decades later, IBM's Deep Blue famously beat Garry Kasparov, the world champ, in '97. We absolutely hit the specific target, beat the human champion.
A huge milestone.
A huge milestone.
Right.
Or as Chollet and many others argue, in the process we learned basically nothing about intelligence in that broader, fluid sense. Deep Blue was a magnificent search machine, a specialized calculator, not a thinking machine.
Hit the target, missed the original point again.
Tragically missed the point that motivated the whole thing.
And this connects right back to the AGI dilemma, doesn't it? For
Yeah.
decades, AI research was mostly chasing task-specific skill, because that was kind of our working definition of intelligence.
Exactly. And that definition, while undeniably valuable economically, fundamentally only leads to automation.
Which is what we mostly have now.
Yeah.
Powerful automation.
Incredibly powerful, but ultimately limited systems. Automation is fantastic for productivity, for taking over repetitive, defined tasks. But what we actually want, what AGI is really supposed to be about,
Is invention, discovery.
is AI capable of autonomous invention. We don't just want to automate known tasks faster. We want AI that can genuinely tackle humanity's hardest unsolved challenges, accelerate science into unknown territory, expand the boundaries of knowledge itself.
And to get that, we need a different target.
A radically different target.
Right.
We need to stop optimizing just for skill the output and start rigorously targeting fluid intelligence itself, that dynamic ability to adapt, innovate, invent. As engineers, measuring what you truly care about, that's the only way to make real, profound progress.
Okay, so if we need a better target, a more sensitive signal pointing towards fluid intelligence, what does that look like? Which brings us back, of course, to ARC1.
Exactly, which Chollet released in 2019 as his first attempt at creating exactly that, a better, more accurate measure. Something like an IQ test, but for both machines and humans.
Right, and you said it has 1,000 unique tasks. That unique part is key.
Absolutely crucial. It means you cannot just cram or memorize patterns or solutions. Each task presents a genuinely novel problem. It forces the system to figure it out on the fly using general intelligence, not rote memorization.
And it's based on simple concepts.
Meticulously built entirely on top of what he calls explicit core knowledge priors. These are fundamental concepts any young child already gets.
Like objects, basic physics.
Objectness, yeah. Elementary physics like gravity or basic object interactions. Simple geometry, topology like connectivity, basic counting. Things a 4-year-old has mastered effortlessly.
So it requires very little specialized knowledge and AI would need to be prepped for.
Exactly. It minimizes the need for specific fine-tuning on the benchmark itself.
So it's designed to be fairly easy for humans, even kids, but incredibly challenging for advanced AI. Which, yeah, seeing a kid solve something a billion-dollar AI struggles with, that must have been that big red flashing light.
Precisely. A stark, undeniable signal that new ideas were desperately needed. It screamed that our scaling methods, while great for skill, weren't producing genuine intelligence.
But it's important to understand ARC's purpose, right? It's not the final definition of AGI.
Vitally important.
Yeah.
ARC is not meant to tell you if a system is AGI, nor is solving ARC the ultimate final goal in itself. It's a tool.
A diagnostic tool.
A precise diagnostic instrument, designed to direct research attention towards what Chollet and his team see as the most important, stubbornly unsolved bottlenecks on the long road to AGI. It's like an arrow pointing in the right direction, showing where the fundamental breakthroughs still need to happen.
And the conclusion from ARC1 was pretty clear, wasn't it? It just completely resisted that scaling approach.
Emphatically. Even after that massive 50,000x scale-up of pre-trained base models, their performance on ARC stayed stubbornly near zero, stuck.
So the takeaway is,
We can decisively conclude, fluid intelligence does not magically emerge just from scaling up pre-training, no matter how big the data or the model. To show genuine fluid intelligence, you absolutely, unequivocally need test time adaptation.
and ARC was the benchmark that showed this.
Crucially, yes. When that pivotal shift to TTA started happening last year, ARC was basically the only benchmark at the time, providing a clear, undeniable signal about this huge paradigm shift. Other benchmarks were saturated.
Saturated, meaning?
Meaning they couldn't really distinguish anymore between a true increase in intelligence and just better memorization or fitting the test set. They topped out. ARC cut right through that noise because it demanded novelty.
Okay, so now people might be asking, if ARC1 showed human-level performance with that OpenAI o3 model you mentioned, does that mean we suddenly have human-level AGI? Are we there?
Not quite. And this is really important nuance to grasp. That graph showing O3 hitting human level on ARC1 can be a bit deceiving if you don't have the context.
How so?
ARC1, by its design, was kind of structured as a binary test, a minimal version of fluid intelligence, almost a presence or absence indicator.
Okay.
So it really only gives you two main modes.
Yeah.
Either you have basically no fluid intelligence and you score near zero like the base models did, Or you demonstrate some non-zero fluid intelligence and you instantly score very high, like O3 did.
And humans are always high.
Right, every human scores near 100%. So while O3 showed human-level performance on ARC1, that benchmark effectively saturates. It maxes out way below the full spectrum of human intelligence. It tells us, yes, you have some, but not how much, or how good is it really?
Which clearly means we needed a better tool, a more sensitive instrument, something with more bandwidth for evaluation, right? To compare against the huge range of human intelligence.
Exactly. And that tool is ARC2, which was just released in March of this year, 2025.
ARC2, how is it different?
Well, if ARC1 brilliantly challenged that dominant deep learning paradigm, large models doing static inference, ARC2 goes further. It specifically challenges the more advanced reasoning systems and actually probes the limits of the TTA pattern itself.
Okay. Same format, though. Input-output pairs.
Still uses the input-output pair format, yeah.
Yeah.
Similar visually to ARC1, but there's a much greater, more deliberate focus on probing compositional generalization.
Okay, ARC2 is all about compositional generalization. Unpack that for us. Why is it so important for AGI? What does it look like in these tasks?
Absolutely. So imagine you teach a child two separate things. You show them a red ball, and then later you show them a blue car.
Okay.
Compositional generalization is that profound ability to then understand and correctly identify a blue ball or a red car, even if they have never, ever seen that specific combination before.
Combining known concepts in new ways.
Exactly. It's about combining known concepts or rules into novel structures, understanding the underlying abstract properties like redness or ballness, rather than just memorizing specific examples or pixel patterns.
Being able to break things down and recombine them.
Precisely. Break down a problem into parts, understand the parts, and then recombine them in new, meaningful ways to solve a novel problem. Current AI models often struggle badly with this.
How so?
They might be great at recognizing all the red balls they were trained on, but ask them to generalize to a red pyramid after only seeing red balls and blue pyramids, and they often fail. Because they haven't truly learned the abstract concept of redness that can be flexibly composed with pyramidness.
Ah, I see. They memorize the whole, not the parts and rules.
Often, yes. And ARC2 tasks are meticulously designed to force this kind of compositional reasoning, to push beyond simple pattern matching.
And how does that translate to the tasks themselves? Are they harder for humans too?
The tasks in ARC2 are definitely more sophisticated than ARC1. In ARC1, for many tasks, a human could just look at it and instantly see the solution, almost like a flash of intuition. With ARC2, all tasks require some level of deliberate thinking, a series of sequential compositional steps. You have to reason it out more consciously.
But still doable for people.
But here's the crucial part. They still remain very feasible for humans. And we know this with high confidence. We rigorously tested 400 random people in San Diego over several days.
Regular folks.
Totally regular folks. Uber drivers, students, unemployed individuals, not AI experts. Every single task was solved by at least 2 people, which shows they are human doable.
Okay.
And even better, a group of 10 people just using simple majority voting on their answers scored 100% on the entire benchmark.
Wow, so that's definitive proof. Humans can do this.
Definitive proof they're solvable by regular people with no special training, just using their innate fluid intelligence and compositional reasoning.
Okay, so given ARC2's focus on this vital compositional generalization, how well do the current state-of-the-art AI models actually perform? What's the gap now?
The performance tells a very clear and frankly sobering story. It really reinforces that we need more breakthroughs.
Okay.
If you take the base models, the big pre-trained ones like GPT 4.5, Llama 4, Simple Answer, 0% accuracy on ARC2, zero.
Still zero,
Yeah.
even the biggest ones.
Still zero. There's just no way to do these tasks via memorization or having seen them in training. They are truly novel.
Okay, what about systems using reasoning, like chain of thought?
If you look at static reasoning systems, the ones using a single chain of thought, so they try to reason step by step, but still without that dynamic test time adaptation, they don't do much better. Maybe 1–2% accuracy, which is basically within the noise margin of 0.
So even reasoning isn't enough without adaptation.
This tells us definitively, to solve ARC2 meaningfully, you really need test time adaptation. And indeed, all the systems that score meaningfully above 0 are using TTA techniques.
Okay, but how well do they do? Are they near human level?
However, and this is the critical takeaway, even with TTA, these systems are still profoundly far below human level on ARC2. Compared to ARC1, ARC2 gives us much more granularity. It lets us evaluate these TTA systems more sensitively, and it reveals that even models like OpenAI's O3 which aced ARC1, are not yet truly human-level in their compositional generalization ability. The gap is still very wide.
So this really confirms it. As long as it's pretty easy for us, for humans, to come up with new tasks that we can do effortlessly, almost without thinking, but AI just cannot figure them out no matter how much compute or data it has, then we simply don't have AGI yet. That's a pretty stark reality check.
It is. Precisely. And in Chollet's view, we'll truly know we are close to AGI, or maybe have achieved it.
When?
When it becomes increasingly difficult, almost impossible, for humans to come up with such tasks. When we struggle to find things that stump the AI.
As long as we can still easily generate puzzles AI can't solve.
We are clearly not there yet. The goal is to close that gap. Make it hard to find those puzzles.
But the journey doesn't stop with ARC2, does it? The goalposts for AGI seem to keep moving.
Not at all. ARC2 isn't the final test either. We've already started significant development on ARC3.
ARC3, when's that coming?
Slated for release early 2026, with a developer preview hopefully July 2025. And this benchmark represents a significant conceptual departure from ARC1 and ARC2.
How so? No more input-output pairs.
It moves beyond that static format almost entirely. ARC3 will be focused almost entirely on assessing agency. Meaning an AI's ability to explore, to learn interactively, to set and achieve goals autonomously, all within novel, unpredictable environments.
So you drop the AI into a brand new world, like a game it's never seen.
Exactly. Doesn't know the controls, doesn't know the goals, doesn't know the physics or mechanics. It has to figure out everything on the fly. Starting with the most basic question, what am I even supposed to do here?
Wow, that sounds incredibly challenging, far beyond just solving a static puzzle.
It is. Every single game-like environment in ARC3 will be unique, just like ARC12 tasks. Built only on those core human knowledge priors, hundreds of these interactive reasoning tasks.
And you mentioned efficiency earlier.
Crucially, yes. Efficiency is central to ARC3's design. Models won't just be graded on if they solve a task eventually, but fundamentally on how efficiently they solve it.
Fewer steps, less wasted effort.
Exactly. Strict limits on the number of actions allowed. Targeting the same level of action efficiency humans show, the system that solves it fastest with the least fumbling around is considered more intelligent.
Forcing human-like learning efficiency, not just brute force trial and error.
Precisely. Pushing away from solutions that just rely on burning massive amounts of compute through trial and error.
Okay, so if TTA is a huge leap, but still not enough for ARC2, let alone ARC3, what will it really take? What are we still missing beyond TTA to get to AGI?
We need to circle back again to the very core of Chollet's definition of intelligence. Remember,
the efficiency of using the past for the future.
Right. Operationalizing past experience for a changing, novel future. The crucial insight here, the sort of philosophical bedrock for future AGI, is what Chollet calls the kaleidoscope hypothesis.
The kaleidoscope hypothesis, that's a beautiful name. What does it propose?
It posits this really profound idea that nothing is ever truly novel.
Nothing is truly novel, but everything feels new all the time.
Exactly. While our conscious experience feels like unending novelty and complexity, every moment, every situation feels unique. The universe itself, at a deeper level, is fundamentally made of many different things that are all, in some sense, similar.
How so?
One tree, though unique, shares fundamental tree-ness with another tree. The principles governing a neuron show fascinating similarities to electromagnetism. Hydrodynamics can surprisingly echo gravity dynamics. We're surrounded by what scientists call isomorphisms.
Similar underlying structures or patterns.
Yes, manifesting across vastly different phenomena. So the kaleidoscope hypothesis suggests that the number of truly unique atoms of meaning, these fundamental, irreducible building blocks needed to describe all this apparent novelty, is actually very, very small.
So everything complex is just a recombination of simple building blocks.
Everything around you, every complex situation, is ultimately just a recombination of this finite set of fundamental atoms, like a kaleidoscope creating infinite patterns from a few bits of colored glass.
Wow. Okay, what's fascinating here then, what this implies, is that intelligence is precisely the ability to do that recombination.
Intelligence is the ability to deeply mine your past experience, identify these reusable atoms of meaning, these invariances, structures, repeated principles, and then, crucially, combine them on the fly in novel ways to make sense of and adapt to entirely new situations.
These atoms are abstractions.
These fundamental reusable atoms are abstractions. Think about how kids learn. They don't memorize every sentence. They learn core concepts: dog, ball, throw, run these atoms. And then they can combine them to understand, throw the ball to the dog, or run after the ball, even if they've never heard that exact phrase. It's compositional understanding, mining those fundamental reusable patterns.
That makes sense.
Precisely. So implementing that kind of intelligence, building systems that truly show this fluid, adaptive behavior, it's going to require two key interconnected parts.
Okay, what are they?
First, abstraction acquisition. The ability to efficiently extract those reusable abstractions, those underlying patterns, from your past experience, from data, distilling general principles from specific examples.
And second,
on-the-fly recombination. The ability to efficiently select the right building blocks from your library of abstractions and then combine them in novel ways to create new models or solutions fitted perfectly to the current, maybe unprecedented situation.
And efficiency is key for both.
Absolutely crucial. How intelligent you are isn't just whether you can eventually do something, it's how efficiently you acquire those abstractions and how efficiently you deploy them. Data efficiency and compute efficiency.
Okay, at this point it becomes crystal clear why just making models bigger and feeding them more data didn't automatically lead to AGI. We are missing these two critical parts.
Indeed, we were missing a couple of critical things that scaling alone just couldn't provide. First, those older models. Despite learning a ton during training, acquiring loads of useful patterns, they fundamentally lacked the ability to do that on-the-fly recombination at test time. During training, sure, they built up this vast internal library of abstractions, but at inference time, they were largely static.
Just fetching pre-recorded templates.
Pretty much. Fetching templates were just interpolating within their training data. They weren't creating genuinely novel solutions on the spot. That was a critical foundational problem.
And TTA addresses that.
And test-time adaptation is precisely designed to address that problem. TTA adds this crucial on-the-fly recombination capability. That's a massive conceptual leap forward, gets us much closer to actual AGI.
Oh, but that wasn't the only problem, was it? You mentioned efficiency. Even with TTA, there's still this huge efficiency gap.
No, not the only problem. The other major issue, even for our most advanced TTA systems today, is that these deep learning models are still incredibly inefficient at the first part, abstraction acquisition.
How inefficient?
Consider gradient descent, the main learning algorithm. It needs truly astronomical amounts of data to distill even simple, common-sense abstractions. We're talking roughly 3 to 4 orders of magnitude more data than humans need for the same concept.
Millions or billions of examples versus maybe a handful for a human.
Exactly. Millions, sometimes billions of examples for a model to learn something a human child might grasp in just a few instances. That's wildly inefficient.
And even the latest TTA systems.
Even state-of-the-art TTA, while powerful, still needs like thousands of dollars of compute to solve ARC1 at human level. And that kind of cost just doesn't scale well to the much harder problems in ARC2.
So the core issue is still this missing compositional generalization and efficiency.
Fundamentally, yes. Current deep learning is still profoundly missing efficient compositional generalization and abstraction acquisition, which is exactly what ARC2 is designed to rigorously measure and expose.
Okay, this is really important. We've been talking about abstractions, but you're saying there's more than one kind of abstraction?
Absolutely. While intelligence is about mining and recombining abstractions, there seem to be two fundamentally distinct kinds.
Okay.
Both types involve comparing instances, merging them into templates, eliminating details. That's the core idea of abstraction. Take things, compare them, find commonalities, drop unimportant details, get an abstraction.
Right, so what's the difference?
The key difference lies in the mathematical domain they operate over.
Okay, step 1.
So type 1, or value-centric abstraction, operates over a continuous domain. It's about comparing things using a continuous distance function, finding patterns in a smooth, continuous space.
What does that underlie in humans?
This kind of abstraction underlies our perception, our immediate pattern recognition, our intuition, that gut feeling.
And this is what current AI is good at.
And crucially, this is where modern machine learning, especially deep neural networks, transformers, this is where they truly excel. Transformers are great at type 1 abstraction. Masterful, really.
Perceiving patterns, language nuances.
Perceiving complex visual patterns, understanding language subtleties, building intuition about data distributions. Their ability to learn powerful representations in these continuous latent spaces is why they've been so transformative.
Okay, so what's type 2?
In contrast, type 2, or program-centric abstraction, operates over a discrete domain. This involves comparing discrete programs, symbolic graphs, logical structures, looking for exact structural matching, logical isomorphisms.
Like logic planning.
This type underlies much of human explicit reasoning. Our logical thought processes, our ability to plan step by step. It's what a software engineer does when refactoring code to find common subroutines, or a mathematician finding a general theorem from specific proofs.
Discrete logical structure.
Yes, and here's the kicker. Transformers, despite all their brilliance with Type 1, they struggle profoundly with Type 2 abstraction.
Really?
This is why you'll find it incredibly hard, almost impossible, to train one of these continuous value-centric models to do very simple yet discretely logical Type 2 things, like consistently sorting a list of numbers without seeing every possible permutation, or correctly adding multi-digit numbers provided just as a sequence of tokens. They don't easily grasp the underlying discrete logical operations in that efficient compositional way.
So it's like that left brain, right brain analogy again, one for perception intuition, the other for reasoning planning.
Exactly. That's a very apt analogy. Type 1 for perception and intuition, Type 2 for reasoning and planning. And all human cognition, all our thoughts, actions, creativity. It arises from a sophisticated, seamless combination of both.
And humans are good at combining them.
What makes human intelligence so powerful is that we're incredibly good at combining them.
Yeah.
Take chess again. You use Type 2, discrete reasoning, when you calculate potential move sequences step by step, but you don't do that for every single possible move. The combinatorial space is way too vast. You'd never finish a game.
Right.
Instead, you only delve deep into a handful of promising options. How do you pick those? You use Type 1 intuition. That pattern recognition on the board built up unconsciously from experience.
So intuition prunes the logical search.
Precisely. You use a Type 1 intuition, that fast, approximate judgment, to make the Type 2 calculation tractable and efficient. That's the synergy we desperately need in AI.
Okay, so if that's the case, how do we finally get to Type 2 abstraction in AI? What's the path forward technologically?
It fundamentally requires leveraging discrete program search, as opposed to purely manipulating those continuous interpolated spaces like current deep learning mostly does.
Program search unlocks invention.
This is the mechanism that truly unlocks invention in machines, moving beyond just automation or pattern completion. And it's not a totally new idea, though its application is getting way more sophisticated now.
Examples.
If you look at all known AI systems today that show some kind of genuine invention or creativity, not just generating similar patterns, but true novelty, they all rely on discrete search.
Even older systems.
Yeah. Even back in the 90s, researchers used huge search algorithms to come up with optimized novel antenna designs for spacecraft. Totally non-intuitive designs.
And more recently,
DeepMind's AlphaGo, that famous Move 37 that stunned the Go world, powered by a sophisticated discrete search through the game tree, guided by intuition. AlphaFold, also DeepMind, revolutionizing protein folding prediction, fundamentally a discrete search system.
So Chollet's point is...
As Chollet succinctly puts it, deep learning doesn't invent, but search does. Search is the engine of discrete novelty.
Okay, let's do a quick deep dive into this discrete program search, because it sounds so fundamental. In traditional machine learning, the model is like a complex, flexible curve, right? A differentiable function.
A very complex curve you're trying to fit to data points.
And learning is gradient descent, which is compute efficient for small tweaks, but needs tons of data. Data inefficient.
Right. Needs that dense sampling of the data manifold to find the optimal shape.
So how is program synthesis different?
In program synthesis, it's almost the inverse, and that's where the power is. Your model isn't a continuous curve, it's a discrete graph. Symbolic operations, like a piece of code or a logical algorithm.
And the learning engine
is combinatorial search, which, unlike gradient descent, is incredibly data efficient. You can often fit an entire program, a complex logical rule, using just 2 or 3 examples.
Wow, just 2 or 3. That's a huge difference.
Massive leap in data efficiency. But the key obstacle, that combinatorial explosion wall we talked about.
Right, the search space gets too big.
You have to sift through a truly vast, often astronomically large space of potential programs. And the size of that space just grows combinatorially with the problem's complexity. Brute force search quickly becomes impossible.
Which is why humans combine Type 1 and Type 2.
This is precisely why human intelligence is so good. We use our fast, approximate Type 1 intuition, our pattern recognition, to manage that combinatorial explosion. We use our gut feeling to prune away the vast majority of bad options before we even start the hard Type 2 logical work.
Okay, so this is the crux then. How does this merger, Type 1 intuition guiding Type 2 reasoning, actually work in practice for building advanced AGI systems? What's the vision?
The big idea, the breakthrough we're really chasing now, is to leverage those fast but approximate judgment calls of type 1 abstraction. All that brilliant curve fitting on manifolds learned from tons of data.
Use the intuition
To fight combinatorial explosion and make that powerful type 2 program search tractable. Use intuition to guide reasoning.
Can you give an analogy?
Think of drawing that map again. Subway stations, discrete connections. Finding paths requires combinatorial search. But what if we embed those discrete stations into a continuous latent space? In that space, we can use a continuous distance function, type 1 intuition, to make fast approximate guesses about which connections are promising, which paths are likely short.
Guiding the search.
It allows us to rapidly narrow down the search space for the type 2 discrete logic engine, keeping that combinatorial explosion in check during the actual precise search for the optimal path.
This really sounds like AI is moving towards systems that are more like incredibly sophisticated programmers themselves, or even meta-programmers.
Exactly. That's the full, ambitious picture. The system Chollet and his team at Tendia are building right now.
A programmer-like meta-learner.
Yes. When faced with a new, unseen task, this programmer-like meta-learner will actively synthesize on the fly a novel program or model specifically adapted to that unique task.
And this program blends different types.
This synthesized program won't be just one thing. It will intelligently blend deep learning submodules, which are great for type 1 problems like perception or intuition, and algorithmic modules designed for type 2 problems like logical reasoning or planning. And this whole dynamic assembly process will be guided by that sophisticated discrete program search system.
Which is itself guided by intuition.
Which itself is constantly informed and guided by deep learning-based intuition about the structure of the program space. It's a system that learns how to program itself effectively for any given problem.
And this synthesis, it doesn't start from scratch every single time, right? It builds on past knowledge.
That's absolutely right. A crucial element. This program search doesn't happen in a vacuum. It leverages a global library of reusable building blocks.
A library of abstractions, those atoms of meaning.
Exactly. A dynamic repository of learned abstractions. And this library is constantly evolving, growing richer, more sophisticated as the system learns from every new task it solves.
So when a new problem comes in?
The system efficiently searches this library for relevant building blocks that might be useful. And crucially, whenever it successfully synthesizes a new, particularly useful building block or a more generalized abstraction while solving a problem,
it adds it back to the library.
It autonomously uploads that new abstraction back to the global library, like a software engineer contributing a useful new function or library to a shared GitHub repository, making it available for everyone's future projects.
Wow. So the ultimate goal here is an AI that faces a completely new situation, something totally unprecedented. And it uses its rich, constantly growing abstraction library to quickly assemble a working model or solution. Much like a human software engineer uses existing tools and libraries to build complex new software without reinventing the wheel every time.
Precisely. And this AI won't just solve new problems, it will keep improving itself over time, both by expanding its library of abstractions and by refining its intuition about the structure of program space. This self-improving, self-programming capability, that's the essence of what they're building at Tendia.
Tendia, François Chollet's new research lab.
That's right.
So let's talk about Tendia's mission then. How does this ambitious vision for a programmer-like meta-learner connect to their bigger goal of accelerating scientific progress?
Tendia's core belief, their driving philosophy, is that to dramatically accelerate scientific progress, to really push the frontiers of human knowledge, we fundamentally need AI capable of independent invention and discovery.
Not just automation.
Not just automation. We need AI that can expand the frontiers of knowledge into the unknown. Not just operate super efficiently within the known frameworks. Deep learning is amazing for automation, but scientific discovery, expanding knowledge, requires something more, that deeper, fluid intelligence.
And their approach is this program synthesis.
Their approach at Tendia is to leverage this unique combination, deep learning guided program search, to build this programmer-like meta-learner.
What's their first big milestone?
Their first significant milestone is to solve ARC, and eventually ARC2 and ARC3. Using a system that starts knowing nothing specific about ARC's structure or tasks, relying purely on its general learning and extraction capabilities, proving the core approach.
And the ultimate goal.
But ultimately, their profound, audacious goal is to leverage this system for science itself. to empower human researchers with a truly invention-capable AI partner. And by doing that, help accelerate the timeline of scientific discovery for all of humanity, tackling problems we can't even properly conceive of today.
What an incredible journey we've covered today. We've really explored why just raw compute scale and massive data, while amazing, were ultimately not enough for true AGI.
Right. The limits of scaling.
We've understood how this emergence of test-time adaptation represents such a crucial, pivotal step forward, letting models adapt dynamically.
A necessary piece of the puzzle.
And we've really delved into this profound, paradigm-shifting redefinition of what intelligence truly means. Moving beyond static skill to focus on the dynamic process, this deep dive has really unpacked that evolving, complex path towards AGI.
And we've seen that the real path forward, the true frontier now, seems to involve this sophisticated synergistic combination, different forms of intelligence working together.
The intuitive pattern matching of deep learning.
Our type 1 abstraction, merging with the rigorous logical inventive power of discrete programs, search our type 2 abstraction.
And this isn't just about building smarter machines for their own sake.
No. It's about fundamentally accelerating humanity's collective ability to innovate, to discover, and ultimately to solve the most intractable problems facing us.
So wrapping up, what does this all mean for you, the listener? As AI systems move closer to becoming these programmer-like meta-learners with these evolving abstraction libraries, maybe consider this. How might this shift fundamentally change the way you approach learning and problem solving, not just in tech, but in any field that demands real ingenuity, creativity, adaptation? Maybe understanding how machines might get to AGI offers insights into how you can become a more efficient, inventive problem solver yourself.
That's a great point. And it raises an important question for some personal reflection, maybe. If intelligence really is about the efficient creation and recombination of fundamental abstractions, finding those reusable atoms of meaning in your experience, what new atoms might be waiting to be discovered in your own unique experiences, your insights? And how might you more consciously leverage them to blaze fresh trails in your own life, your career, your intellectual pursuits, just as these AI systems are now learning to do?
This was the GIST podcast. If you liked it, please leave a like and subscribe to this channel.